And I will just start with our contribution entitled to New GNSS bias products from the Center for Orbit Determination Europe. I also have to acknowledge the co-authors, in particular Arturo Villiger, who did the software implementation, presented and highlighted at the Sydney workshop, and also the reprocessing E4. The new bias handling has been implemented in the bonus GNSS software and activated finally in May last year in all analysis line. Another important aspect was that we took this as an opportunity to review and completely redesign all bias relevant processing steps. An important point is also that our new bias implementation allows to combine the bias results on the normal equation level. So this means that we're able to combine biases from the clock analysis, where we rely on the ionosphere-free linear combination, also from the ionosphere analysis, where we rely on the geometry-free linear combination. And also an important point, I will show the results later, is to compute coherent long-term code bias solutions. All bias products are made available in the new bias Sinex format version 1.00. An example file you may find here. This is, as we typically produce, a sliding 30-day combination. Here indicated is in red is that the FTP server address has changed, so the old address is still valid, but will soon you will have to use the new as a name. So the bias parameters are treated specific to each observable type involved. So this means they are treated at the pseudo-absolute level. So mentioned, the thing is activated in the operational GPS GLONASS analysis and also in the MJAX 5 system analysis since the end of January this year. This is an example of this observable specific code biases as obtained for the GPS constellation from the clock analysis. And what you see here is indicated with these boxes. So these are the reference observables. And here you see the clock convention. They are assumed to be 0. And what you nicely see is when you add the information from the ionosphere analysis, then you can separate that. So this is then a set of bias for the GPS constellation. Here, this second group corresponds to the block 2F generation. This is again the same plot, and now compared with the results from the MJAX analysis. And what we see here is there is a generally very good agreement between both results. This outlier comes from the fact that this particular satellite was unhealthy during that time. So we already have a prototype to do ionosphere analysis with 5 or more systems. And here are the biases now for all signal types involved for GPS. To give an example also for GLONASS, Galileo, Beidou, QZSS. So you see we have a set of pseudo-absolute biases for all systems, all signals. The GLONASS biases in our operational solutions are treated typically common to each satellite station link. And for monitoring purposes, we also do this treatment for GPS. So what you see here is for each station, you have a bias for each station, each satellite. We reduce the mean bias and we plot the values. And here you see this satellite-specific patterns. And this somehow does legitimate that we can separate the biases into a satellite component and a receiver component. Interesting is when we do this for clonals, there is commonly a wider spread, but this somehow shows that for a zero-order correction that we also can produce satellite-specific and receiver-specific corrections to the user. And the nice thing is we can do this transformation on the normal equation level. But somehow striking are these outliers. And we found that these come from stations equipped with this particular receiver. The good news is that Ken will tell you that it seems that the problem could be solved. He will tell the reason. Considerable achievement of our work was a bias-dedicated reprocessing effort over 23 years. So here you see the 3 steps. So the actual reprocessing, the bias, the outcome is bias results, and also global ionosphere maps. Then the second step is the computation of a coherent long-term solution at neck level. And the third point is to realign all daily estimates with respect to this series. And this graph nicely shows, or gives you an overview over the GPS constellation over more than 2 decades. So you see here the space vehicle numbers, the older vehicles up to the newer vehicles, and the time axis. And the remarkable is, on one hand, how stable the biases are. Then, and the other thing you also may notice that there are reactivated satellites. So a typical, so I guess the first example was SVN23. So with a reactivation test and then reactivated over several years. Now the 3 series. So this is the original series we have. So if you take this the result from the operational analysis, you may notice this behavior. So you have a datum definition specific to each day with the zero mean assumption. So you see common signals, variations just coming from appearing, disappearing satellites, changing values, etc. So you cannot interpret these values. Having a combined set without considering discontinuities, you already see this kind of series, very stable over time. Then you see here jump events, here, etc. And when we consider these jump events, then you end up with a pretty nice long-term series. And this is really a unique achievement. Again, you see here the difference between the original series with no jumps and then between these 2 series. And I added here some examples. So, for example, this particular satellite with reactivated periods. And what you also nicely see is that we treat internally for each activation interval a specific parameter. We also could see a certain kind of trend. We also have an additional feature that we can constrain then all values with respect to the to one SVN number, so that we end up with a constant here. Oh. Going up, going again down, reactivated very long, so it's remarkable how long the lifetimes are. Strange behavior for this particular satellite, very stable with some events. And this particular satellite also shows some kind of different levels, but typically very stable with jumps. And here is a listing of these jump events. The nice thing is that you can, for many of them, attribute them to specific nano messages. A byproduct of this reprocessing is a ionosphere. So this is the mean TC from our operational solution. And this is that one from the reprocessing effort. With one more year, So as a byproduct, we have in addition more than 200,000 hourly global ionosphere maps. Now we have the DCB multiplier method we had generalized that in the following sense. So this is a method to verify Reinex data to which receiver class the data set belongs to. And I try to show how this works. So this is a key. You have 6 notches, codes. So the code for this key is like this. We just replace the notches by the space vehicle numbers and the codes by the code bias values. And you remember that you have these typical patterns for each observable type. And this is exactly what we do. So we set up a set of scaling factors. We call them multipliers with respect to all known SVN-specific code biases, plus at least one station-specific component for a particular linear combination, and the estimated parameters are here underlined. So it's a kind of pattern matching, and this plot shows results. So we analyzed the data from a big set of stations. Here you see the receiver names here. Then the observable one, the first and the second observable, color-coded with these types here. And as it was the geometry 3 linear combination, as soon as you have a 1 plus 1, it's the found observable type belong to this actual observables, and minus 1 is the second observable. So this works pretty well for GPS and also other systems. I mentioned the format is bias Reinex version 1.00, and this format is available. Our side and DLR does support the new format. The GFZ group and the Chinese group still rely on the old format. So this is the summary. We implemented a refined bias scheme for all analysis lines. The new bias Reinex is supported. Then I mentioned the remarkable reprocessing effort concerning biases and ionosphere, where we end up with a common code bias datum, and this is really unique. So you can understand this as we have the iteref for the coordinates, so to have a unique datum. Then the GLONASS receiver code bias anomalies, it is planned to develop an automatic detection tool to find these outliers. And finally, I highlighted the generalized GNSS code bias multiplier method. The reprocessed ionosphere series will be made available, and I also mentioned the prototype. So if you have questions and inputs, this is then welcome for the Splinter meeting held on Thursday afternoon. Okay.